Good morning, everybody. We're just about to start now our presentation on how to combine materials to optimize performance with Charlie Bream from Granta and Benjamin Hornblow from Force Technology. We will first have Charlie presenting from Granta, and then we will have Ben, who we can see on this slide, showing how he has used the Granta CES Selector software to design a longboard, which is a type of skateboard. So now I'm going to hand over to Charlie and we will start the webinar.
Okay, thanks, Anne. Today's topic is really about how to combine materials to optimize performance. So a lot of this is about combining two or more materials to optimize the performance of your product. So what I want to do today is really to show you the capability within CES Selector, and to do this I'm going to carry out a product case study to show you the tools and the data that we have. So I'm going to basically work around a scenario. So I'm going to say I'm a material specialist. I'm working in an automotive manufacturer making body panels for the cars. I'm going to say that we're currently using steels. This is obviously the main material used for body panels at the moment. But there's a focus at the moment to reduce mass, and this is all driven by the need to reduce environmental impact, reduce emissions from the vehicles. I'm also aware that smart cars for a number of years now have been using polymer-based door panels. Polymers are typically lighter than metals. I want to really understand, should we be using this type of material for our product? And also, we're interested in reducing the environmental impact of the product. So, can we actually start to incorporate, natural fibres into the materials, have a composite to both reduce the weight, but also to increase the, reduce the environmental impact of the product. So I've been tasked with identifying a new lightweight material, which is also environmentally friendly. So this is the scenario. Obviously, here we're currently using steels. We're looking to start utilising new materials. This brings around a number of challenges. The first thing here is, which polymer. Smart have been using a polymer. It's a polypropylene-based material. So I want to understand which polymer should I be using. Should I actually be using polymers at all? Is there another material out there which is better for the application? If we're looking at natural fibres, there's many different types of natural fibre. Which is the best one to be using for the product? Also, where can I find data on these materials? Obviously, I have a lot of data on the metals, but here I'm starting to look at new materials. I need to have access to data on these alternative materials. The other thing is, if I'm starting to look at composites, maybe sandwich panels, which configuration is best? Obviously, as soon as you start combining materials, there's almost an infinite number of combinations of how you can combine those materials. So which configuration is best? This is both fibre loading level. If I'm looking at a sandwich panel, the skin to core thickness, the different materials I can use. Also, obviously one of the key things here, if I'm starting to use composites or sandwich panels, I want to make sure that the benefits I get outweighs the additional cost. I don't want to spend a lot of time developing a brand new composite, a new material, if there's an existing material out there on the market which performs equally as well. So we really need to understand the performance of current materials as well as the ones I'm going to combine into a composite or a sandwich panel. So the key thing is, where should I focus my development efforts? So these are the things that we're trying to address with CES Selector. It's all about providing you access to data on materials and tools to help you start to explore, if I start combining different materials, how are they going to perform? What benefits are they actually going to give you? So the starting point for most designs is to define your design requirements. So here for this door panel, I'm just going to define these in terms of the function, objectives and constraints. So if we look at our door panel, in very simple terms, this is a panel. It's a stiffness limited design. If someone presses on the side, we don't want it to deflect too far. because it'll damage equipment stored within the door panel. We're also going to say that the length and width is obviously fixed by the design, but we have some freedom to change the thickness. So this is the function. This is basically the geometry and load condition on my material. We then have a number of constraints. So these are critical criteria which the material must satisfy to simply operate in the environment. So it has to have resist the temperature, any chemicals it's going to come into contact with. It's got to have adequate strength and toughness. If it gets hit on the side, we want it to fail in a brittle manner. We want it to fail in a ductile manner. And also there's going to be some constraints on how we process the material. So if we're producing it, say, a metal, we're going to produce it from a flat sheet. Whereas if we're going to produce it from a polymer, we're probably going to use some sort of moulding process. So these are the critical things which the material must meet. And our objectives here, my primary objective is to minimize the mass of this component, but also I want to consider the cost of the new material. So this is the scenario, and what I'm going to do is I'm going to dive straight into the software and start to look at what materials I could utilize for this application. So my starting point is really to consider, what are the current materials, where does my current material lie relative to others, and then I'm going to investigate, the use of composite materials. Can I use natural fibers? What benefit will a natural fiber reinforced material give me over conventional materials? So to do this, I'm going to use the Material Universe dataset. This is a unique dataset which covers all classes of engineering materials. So here I'll just highlight a few of the main ones. So today I'm interested in natural fibers. So here you'll see we have data on the whole range of different natural fibers. If we're interested in sandwich panels, we have a lot of information on foams and honeycombs. So this is obviously important if we're trying to lightweight materials through the utilization of those materials. We also have a lot of information on the metal alloys. So here today I'm going to say that our current material that we're utilizing for our door panel is actually a drawing quality cold rolled steel. So this is our current material. This is the data sheet. This is a very typical data sheet for a material in the Material Universe. I'm not going to go through it, but one of the key things about this is we have complete and comparable data for all the materials within the Material Universe. And what I'm going to do is I'm just going to set this material as the reference. So this is our current material. This is the material I'm trying to improve on. So we have a whole host of full coverage of the different metals and alloys. And also we have, as you expect, coverage of elastomers and also the thermoplastics. So I'm simply going to go down to the thermoplastic, which Smart are using. This is a polypropylene. It was a talc-filled and a copolymer. So this is the data sheet for the material that Smart were using. So it has a similar type of data sheet. It's complete and comparable data. For this, I'm just going to add this to favorites so I can actually highlight this when I come to create some property charts. So these are the two materials which I kind of started off. I've got my reference material, the material that Smart's been using, and I want to compare those against all other materials in the database. So to do that, I'm going to start by considering all bulk materials. So this is over 3,000 materials, and I'm going to start by just plotting my function and also my objectives. So we are saying that this application was a panel, it's loaded and bending, it's a stiffness limited design, and we're looking to minimize the mass. And this tells us to minimize the mass of this panel, stiff panel load and bending. We need to select materials with low values of this index. So this is density divided by the flexural modulus to the third. But what I'm also going to do is I'm going to plot this against the objective to minimize the cost of the component. So what I'm doing here is I'm basically defining or creating a trade-off between mass and cost for this particular panel. So if I do this, we get a mass cost trade-off. So here's our mass per unit of stiffness against cost per unit of stiffness for all materials in the database. Our ideal material will be in this bottom left-hand corner. At the moment, we're looking at the full Material Universe, so we have everything included here. So we've got woods, foams, concretes. Obviously these wouldn't be used in this application, but I can very quickly identify where my current material is. So what I'm going to do is quickly filter this database based on my constraints. These are the critical criteria which must be met to meet just to simply function in the application. So I'm going to quickly run through these. So we had a requirement on the yield strength to be greater than 25 megapascals. If I apply this, then it starts to filter the database. So this is eliminated 300 to 400 materials, and I'm going to go down and apply similar constraints for all the different materials. So ductility index relates to the likelihood that the material will fail in a ductile or a brittle manner, and I'm basing this on the value for my current material. It also needs to operate between 80 and minus 20 degrees C, and it also needs to resist a couple of chemical environments. So here we had fresh water, so here we want this to be acceptable and excellent. This is the value for the current material. And also organic solvents, so this is to represent fuels and lubricants which it could come into contact with, and I'm going to apply those constraints. So this is now dropped down to roughly 50% of the database. The final thing I'm going to apply constraints on are the processing requirements. So here I was going to say that we're going to process this. Maybe if we're going to use composites, we use composite forming processes. If we're going to produce metal sheet, it's going to be formed from a sheet forming process. And using the polymers, then we're going to use polymer injection molding. So it's going to select those different processes, and this further filters down the data set. So now if I come back to my original chart, all the materials which have failed these additional constraints have been greyed out, and I can very quickly hide those. So now I'm really getting a good indication of the materials which could be appropriate for this particular application. So here we can see the steel. This is very good in terms of low cost, but it's certainly not the lightest weight solution. I can highlight a number of materials. So these are the aluminium alloys, the magnesium alloys. There's a polymer here. This is a PA66 with carbon fiber, and here we have some high performance continuous fiber reinforced composite laminates. So here we can start to see the trade-off, really understand the relative performance. One question is, where does the smart material lie on this plot? I can highlight that. I'd set it as a favorite, and I can see that it certainly gives us some weight saving over the existing material. It's probably about a 35% weight saving, but it's not as good as the aluminium and magnesium alloys. So I might say it could be a good material, but there's certainly opportunity to have lighter weight solutions. So this is kind of a starting point, is really understanding how the different materials perform relative to each other. But what I want to really do in this webinar is talk about how can we start to combine different materials to optimize the performance. So what I'm going to do is say, well, maybe we can take a polypropylene material. If we maybe add natural fibers to that, how's it going to actually perform relative to the other materials? So that's what I'm going to do. To do that, I'm going to create a new chart, and I'm just going to focus initially on minimizing the mass of the component. So here I'm going to create a chart of the flexural modulus, and I'm going to plot that against the density. So this is, I will create my chart. So here we have flexural modulus against density, and this is currently for all materials. Ideally we're looking for materials with high flexural modulus, low density. So this is up in this blank space. And what I'm going to do is initially I'm going to say, okay, I'm going to utilize natural fibers, but there's many different types of natural fiber. Which is the best one I should be utilizing? So to do that, I'm going to do a quick study. I'm just going to focus in on those materials. So I'm going to create a custom subset. So here I'm going to say, well, for the matrix, I'm going to use a polypropylene. This is the smart material was based on a polypropylene. It's a cheap matrix material. So in a way, it's a prime candidate to use for the matrix. So I'm going to select the polypropylene. This is the matrix I'm going to use, and I'm going to focus in on the natural fibers. So I'm interested in all the natural fibers, and just for reference, I'm interested in E-glass. That's a very common reinforcement for composites, and also the carbon fiber. So I'm going to select a high strength carbon fiber, and I'm going to create this custom subset. So this is basically, I suppose, the starting point for my analysis. Down here I have my polypropylene matrix. These are the natural fibers, and these are the glass fiber and the carbon. Up here I have my current steel material. So what I want to do is really understand, if I start combining my natural fibers with my polypropylene, which is going to give me the best performance. So one of the things I can do is I can add an index line onto this chart, and the index with a slope of 3 is the correct one if this is a panel loading and bending. And the key thing about this is that every material which lies along this line has the same value of that index. So this says if I essentially mix this polypropylene with, say, this fiber, I'm not going to get much enhancement in performance in terms of this metric. Whereas ones up here are likely to give me much better increases in performance. So the higher this line is up here, then the higher performing the material is. So very quickly, based on this type of chart, I can start to understand which of these materials are likely to give me an enhancement in performance. So it really means I can focus my effort on the right material. So one of the things we can do is we have the synthesizer. So this is the tool for basically combining different materials, and we can very quickly estimate the performance of hybrid materials and structures. So here I'm going to say I'm interested in a quasi-isotropic laminate, and I can specify my matrix and my fiber material. So here I'm going to go for a polypropylene, the unfilled, the homopolymer, high flow as the matrix. And I'm going to look at a couple of fiber combinations. I'm going to look at sisal. So this didn't have that higher performance, but I just want to show the difference. We're going to look at a number of fiber volume fractions between 10 and 50%. And I'm just going to put in a record name. So this is a polypropylene with sisal. And if I click create, it's going to calculate the performance of that composite. So now if I highlight this is my sisal, this is my fiber, this is my matrix, and these are my composites I've created using this analysis. So this, when I look at the line, this is showing there isn't a huge benefit in terms of this index in utilizing sisal material. However, if I repeat this using one of the higher performance materials, if I change the fiber to, say, a hemp or a flax material, then I can really see the benefit. So this is a PP and hemp. So when I do this, rerun the analysis, then we see these are the new materials. So these small bubbles here, this is the performance of the hemp filled material. So we can see there's a big increase in the performance by using a hemp fiber rather than a sisal fiber. This is really important because it means I can focus my development effort on the most appropriate material for my application. So this is a key part of the process. Obviously now what I want to do is actually see how these materials compare against the conventional materials. I don't want to use this material if, say, an aluminium alloy gives me the same performance. So what I'm going to do is quickly change the color of these records so we can see them readily on the chart. So I'm going to change those, the hemp to lime, and also the sisal fibers. So now I'm going to go back to the original chart I had, and I'm going to look at all bulk materials again. So if I come back to this chart, And if I rescale this, then this is the analysis. So I'm just going to zoom in on the area of interest. So our initial material, this is the steel. I can highlight the copolymer, the talc-filled polyprop, which Smart's been using. But very quickly, I can start to see, this was the sisal. This is showing not much benefit, increasing the fibre content. It doesn't really reduce the mass of the component. But I can see that this hemp-filled one is much better, and also it's much better than the aluminium alloys. This is significant weight saving, and it also outperforms the magnesium alloys. So this has given me a good amount of confidence that this material is worthy of further investigation. The next thing we could do is we could actually take this a step further. We could say, okay, let's take this polypropylene hemp and create a sandwich panel. Is there any benefit in doing that? Again, we can use the synthesizer to investigate this. So here we have a model for looking at sandwich panels. So this works in the same way. I just need to define my configuration. So the face sheet material, I'm going to use the material I've estimated. So 50% hemp looks to be a good, or 50% reinforced polypropylene with hemp. And I'm going to use as a core material, I'm going to say, okay, let's take a honeycomb material. I could do a selection project to identify which is the best honeycomb. There's not time for that, but I'm going to select a polypropylene honeycomb. It's the same material as the matrix. I'm then going to specify a face skin thickness. So I'm going to say we're going to have 1 millimeter thick skin, but I'm not sure what thickness of core material to use. So I'm going to look at the range. I'm going to say between 1 and 5 millimeters, and we're going to create a number of different scenarios. I then just need to specify the support and load conditions. So here this has built-in lens. Essentially the ends are clamped on the door, and it has, I'm going to say it has a central load. The span is roughly just under 1 meter, and I can very quickly investigate the performance of this sandwich panel. So this is a PP hemp with a PP honeycomb. If I create this, then it's going to add this sandwich panel onto the chart. So now when we look at this, we can see this was our hemp material, and now when we look at the sandwich panel, we can see that they give significant improvement over the other materials. So very quickly I can start to investigate these different material combinations, get a feeling of how they perform relative to each other, but also relative to standard materials. So this really gives me a lot of confidence in terms of where should I really focus my development efforts. So that's everything I wanted to show in terms of the data and the core tools within CES Selector. I'll quickly summarize within the slides in terms of what I showed you. Obviously, to start with, I looked at the current situation with standard materials. Based on this, I can very quickly identify this is our current material. Going to the talc fill material, I get 35% weight saving, but this wasn't as good as what could be achieved with other commonly used materials such as the aluminiums and the magnesium alloys. So this gave me a good starting point, a good grounding. But then what I did, I went into the utilise the synthesizer to really understand, investigate the potential of using natural fibre reinforced materials. So here I can look at very quickly identify which is the best reinforcement and start to see, how that actually performed against other materials. In this case, it's definitely identified as the hemp and the flax were certainly the best options in terms of performance. And then I can compare those against the standard materials. This was giving, looks very promising, particularly against the aluminiums and the magnesiums. And I can very quickly, identify or investigate, start to consider, if I then take that composite I've just created and start to consider a sandwich panel, what implication that will have on the performance of the product. So that's everything I wanted to show in terms of the data, the tools. I guess one of the key questions is, where do you use this in the design cycle? This is a very typical development workflow. You start off with your requirements. Based on that, you'll come up with a number of concepts. You maybe start looking at different materials, sandwich panel constructions, composites. Once you've happy with what you think is the best, you'll go forward to the detailed design stage. You probably do a number of, you might do modeling, you might do optimization. Once you're happy with your design, then you go forward to the prototyping and testing stage. So this is the time when you start to commit to tooling, committing to materials. Often what you find at this stage is that things don't quite work out as you expected. You often have to go back to the detailed design stage, refine some aspect of the design, maybe change the thickness, maybe add in stiffening ribs, maybe even change your material. Often you go through this process 3, 4, 5 times before you come up with your final design. The idea of CES Selector is very much to help you at the preliminary design stage. It's very much a pre-screening tool. Which material should I be considering before I start to commit to a particular design? These latter stages, this is when the cost builds up in terms of the development costs of your product. So it's very much used pre-screening for materials, investigate different combinations of material in this early stage of design. This is the time when you have the freedom to change your material and also to change your design concept. So many benefits for doing this, and it's really about making you more efficient, more effective when it comes to selecting materials and developing your products. So that's everything I wanted to cover. What I want to do now is to hand you over to Benjamin, who's going to talk about how he's used the data, the tools in CES Selector to develop this lightweight composite longboard.
Great. Thank you for the introduction, Charlie, and good morning, everybody. So, yes, my name is Benjamin Hornblow. I'm a composite specialist for a company called Force Technology. We're based in Denmark. And I'm going to talk about the design of a composite longboard that we did. Here's a quick overview of the agenda, a little bit of background on Force Technology, and then also background on the industry's composite laboratory. Then we'll look at the longboard design and material selection, and then prototype production. So Force Technology, we're an independent, unbiased, non-profit company. We have a development budget of about 30 million euro every year. We have a number of experts working in different areas. We have plastics, polymer experts, steel and corrosion, where we do weld inspections, non-destructive testing, concrete, and also composites. We're a GTS company, which is, it means that we're a certified Danish company. We're more like an institute, actually. And we have a number of government-funded projects that we run here. And we have, a bit of a special relationship, I think, to the Danish government. We're an international company, so we've got headquarters here in Denmark, just outside of Copenhagen. We have offices in Sweden and Norway, United Arab Emirates, China, and Singapore. So what is the industry's composite laboratory? It's a partnership between Force Technology and the Technical University of Denmark and Aalborg University. It's funded by the Danish Ministry of Science, Innovation, and Higher Education. It's been running for 3 years, and we have just received funding for another 3 years. So we're basically a knowledge center that helps small and medium-sized companies produce parts, composite parts. These could be new parts, so they could be switching over from an existing material to a composite material, or it could be a company that's already working with composites, and we help them optimize the design or the production process. And this is what we look like graphically. So we're the hub. We like to think of us as the hub in the composites network. So the services provided, we do material selection, and of course we use Granta CES Selector to help us with that. We do product design, structural analysis, coatings. We have a number of coating experts in-house, and we can do accelerated weather testing. We do product lifecycle assessment. We also have environment experts and experts at doing LCAs. We can help with manufacturing processes and optimizing that, producing prototypes. We're just building a new composite manufacturing facility. So that'll be up and running just after the summer holidays. We can do material testing at the coupon level, but also substructures as well. And we can do damage assessment. We have scanning electron microscopes, so we can look at why things have failed and look at void content and bonding between fiber and matrix. Oh, and we also do seminars and courses. So that's part of our mandate to share the knowledge that we have and the knowledge that the universities have out into the industry. Here are some of the industrial products that we've worked on in the last phase of EcoL. Cargo bikes. So these are quite popular in Denmark. It's a 3-wheel bicycle, and you carry the kids in it and pick up your groceries and stuff like that. Today, most of the designs are quite rectangular, and they use plywood for the side panels. So we toyed with the idea of actually casting the box in one piece and using a natural fiber composite. What we ended up doing as a middle step was to make flax fiber sandwich panels that could be a replacement to the plywood, and we actually saved quite a bit of weight doing that. We worked on some low pressure air tanks. So these are glass reinforced, actually long continuous fiber reinforced nylon air tanks that are used mounted on trucks, and they run the air brakes. So we helped with the production process there. There were some challenges. We also helped the company with their rigid hull inflatable boats. So these are search and rescue boats. They're made in Denmark. They have a mixture of carbon fiber and glass fiber in the hull. And we optimized the design of the hull to make the production simpler. And also we saved weight in the process too. In that case, we did some quite advanced finite element analysis with the universities. So now over to design of a composite longboard. We decided to design a composite longboard because we were giving composite course, and we wanted to make something that was a bit more interesting than just a flat panel. So we came up with the idea of doing a longboard. It's got a little bit of geometry, and it's something that you can functionally test after you've made. So for those of you who aren't familiar, this is what a longboard looks like. It's a long skateboard. It's about 1 meter in length, 230 millimeters wide, thickness of 9 to 12 millimeters. It's usually double curved, so it's concave in the width direction and then convex in the length direction. You can ride them fast, like you see in the picture here. Make sure you've got a helmet on. Or you can ride them slow. I've got one, and I use one for cruising around Copenhagen on the bike paths. And I definitely don't go as fast as these guys. So, I thought for a starting point, I wanted to look at the longboard materials and see what's available on the market. And I bought a longboard in New York about 4 years ago. It's the one on the right. I'll talk about that in a second. But just as a starting point, I was curious to see, okay, well, you can buy different longboards. You know, they're all about the same length and, slightly different widths, different graphics. But what do the materials mean? And is this something that we can improve upon? So the board on your left is your classic maple 5 to 8 cross-ply board. It runs for about $70 to $90. Very popular. Then the one in the middle there is a bamboo board. They're also readily available on the market. And in this case, it's unidirectional ply. So the fiber of the bamboo runs just in the length direction on this board. That's traditionally how it's done. Then the board on the right, this is the one that I own. And being a composite specialist, I saw this board in the shop, and the sales guy told me, it's like, oh, it's got carbon fiber on the bottom and it's got glass fiber on the top. I was like, okay, I'm buying it. So it was a little bit more money, but I thought it was pretty cool. And so what they've done here is they've put some face sheets on the board, and they still have the maple core, and they've been able to reduce the thickness of the board a little bit, but still maintaining the bending stiffness. So this board I decided to use as a reference board. So if we look at the design requirements, Charlie gave an excellent presentation on panels and bending and stiffness-driven designs. So I think I can gloss through this a little bit. We wanted to have the same bending stiffness as the reference board, and we wanted to be able to use existing components, so wheels and trucks, etc. It also had to work in outdoor environments. And for the free variables, we have the thickness, and we also have the material combination. So what sort of fiber reinforcement are we using for the face sheets? What sort of density are we using for the core material? And for the objectives, we wanted to minimize weight, because if you've got a board that weighs less, then it requires less energy to push, to accelerate, and to decelerate. And we wanted to absorb vibration, so we wanted to have a comfortable ride. So that was important for the performance as well. So I'll just talk quickly about technical fibers. And these graphs I've generated in Granta. So technical fibers are used for making composites and making laminates. And there are different kinds. The first 5 in the graph here are all natural fibers. So we have cotton, flax, hemp, jute, and kanaf. I'm not actually sure what kanaf is, but it's natural. Then we have the well-known glass fiber, carbon fiber, and Kevlar. So if we compare just the stiffness, the Young's modulus of the fibers, you can see that the glass fiber sort of lies in the middle of the flax fiber. So the flax fiber is actually pretty good in terms of stiffness. You can't compete with the carbon fiber. That's pretty good stuff. So if you're after stiffness, then you need to be really looking at carbon fiber. The strength side isn't so good for the natural fibers compared to the glass fiber. But that's okay, because in this design, it's a stiffness-driven design. So we're not too worried about that. Another great property with natural fibers is damping. So again, I've generated this in Granta. So we have the mechanical loss coefficient on the y-axis, and you can see that the fiber damping is about 3 orders of magnitude higher than the glass fiber and the carbon fiber. This is why carbon fiber and glass fiber make such good springs, because they don't lose a lot of energy when they're bending. So a common thing to do with composites is to combine the carbon fiber and the flax fiber, because you get the stiffness benefit from the carbon and you get the damping benefit from the flax. The flax is also a lighter fiber, so you can save some weight as well. Okay, I'm going to switch over to the Granta demo now. Okay, so this is a worksheet that I've prepared beforehand, and this is the one that we used for comparing the different boards and the different materials, and then also looking at our final material selection and seeing, okay, well, where does that sit in comparison to the existing materials on the market? I start with the material universe and all bulk materials. And now I'm going to go over to stage 1, where I put in some constraints, and this is what Charlie talked about earlier. I think I can probably gloss over this as well. I have a density constraint of 3,000, so anything heavier than that I'm not really interested in looking at. And I have a Young's modulus stiffness of 1, so anything less than 1 I'm also not that interested in. Then I've got some temperature constraints, and then it also needs to be acceptable to use with water for outdoor applications. So now I'm going to jump over to this menu here and show you some of the special materials that I've created. The first one is a flax laminate, so 35% flax epoxy. I used the material synthesizer to generate this material. I also generated a 5-layer material. So this is a tool that Charlie didn't show, but it's a multi-layer material. And in the synthesizer, you can create materials with up to 7 layers and mix your materials together. So what I've done here is I've created my 5-ply maple board with different fiber directions, 0 and 90 degrees. I've also created a 7-layer material, this one here, which is my board, the reference board, and this has the E-glass on the top, then it's got maple layers, and then carbon fiber on the bottom. I've also created a sandwich panel. Being a composite specialist and working with projects that involve lightweight design, I'm familiar with sandwich panels and the benefits that you get in terms of light, stiff structures and bending. So therefore, I created a sandwich panel using a 1 millimeter, I think I can probably show that, carbon fiber face sheet, unidirectional, and then various thicknesses of the core, and that's a PET foam core that I'm using. So if I jump over to stage 2, you can see these are all the materials that I've just ran through. They're marked as my favorites. And on the y-axis, I have flexural modulus. So this is bending stiffness. And on the x-axis, I have density. And the slope of my line here is 3. So this is giving me the performance index for comparing light, stiff panels and bending. So this is the direction we want to go. So materials above the line here are going to be better performing in this application. So you can see that here's my flax fiber laminate. So if I was just to make the board out of flax fibers and epoxy, then it's not going to be as good as the maple board that you see today. Here is bamboo, and you can actually see that, well, bamboo's pretty good. Bamboo's better than the maple. And this little dot here is my board, the one I bought in New York, and I was disappointed to see that, well, actually I could have saved some money. I could have just bought the bamboo board, because in terms of performance, it's about the same. So I've also plotted the sandwich panel, the carbon fiber sandwich panel over here. So when I looked at this graph, I said, okay, well, there's definitely room for improvement between these two boards and the sandwich panel here. So based on that, and the materials that we had readily available in-house, we had carbon fiber fabric, we had flax fiber fabric from working with the cargo bicycle. We measured the mechanical properties, so we knew what the stiffness and the density was of these materials. I decided to create another 7-layer layup, and I'll show you that here, where we have carbon fiber twill as the outermost layer, UD carbon fiber, and then flax biaxial fabric. So those three layers together create the face sheet. Then there's a foam core, and then you have the same face sheet on the other side. Now this is really based on experience, and I performed a hand calculation to make sure that I match the bending stiffness, so that the bending stiffness of this configuration here would be the same as the reference board. So now if we plot the new board, the new design on stage 3, you can actually see that it lands up over here. And this is, wow, this is a big jump from the bamboo and the e-glass board, and approaching what I would say is sort of, you know, an idealized design in terms of a sandwich panel over here. So it was great to use the multi-layer tool in the synthesizer to be able to see, okay, yes, this material is, this combination is going to give us a much better performing skateboard. Okay, so now back to the presentation. I'll just quickly take you through the manufacturing process. I think it'll give you a better impression of what this board is like. So we modeled the skateboard in CATIA. It's our 3D CAD program. It has a length of 40 inches, width of 9.25, and a thickness of almost half an inch. Longboards are typically measured in imperial units, so that's why they have sort of funny metric equivalents. And then here is the form that we had CNC machined. It's made from a material called Sika block, and it's cheap and great for producing prototypes. So here you can see the form, and you can see the fabric layers being put into the form, and then the core material. And once that's all packed together, then you put the foam on top, and you infuse, so you pull a vacuum on the form, and you draw the resin in through the material. Then you allow that to cure, and then you can demold it. Then there's a trimming process. Then we did some validation and testing. So we measured the bending stiffness of the board. And we made a few boards, and so we cut a cross-section out of one of them. So here you can see the PET foam core, and you can see the flax fibers, which is the lighter color fibers here. And you can see the carbon fiber. I'll also mention with the flax fiber that we had the fiber orientation at plus and minus 45 degrees. This gave torsional stiffness to the board, which is also important. So not only is the flax dampening vibrations, but it's also giving us some torsional stiffness. Then there was some assembly, and then of course the test. So there's a picture of me riding the board, almost crashing into the rubbish containers there. We didn't have a lot of room beside the facility where we made the board, but I had enough to turn a fairly tight circle. And the board felt great. It felt really good, actually. The stiffness was about right, and it was very comfortable to ride. Okay, so now the results. So we're a little bit thicker than the reference board. We came out to 11 millimeters, which is still totally acceptable in terms of our thickness range. But the weight, look at the weight. We dropped from 1685 grams down to 1180. So we saved half a kilogram on this board. Deflection, it was a little bit, deflected a little bit more in 3-point bending, but not much. It was totally acceptable, I think, in terms of the stiffness. So that was actually a 43% weight savings. We're very happy about that. Yeah, so in conclusion, we had a bending stiffness similar to the reference. We saved 43% weight. We had good finish on the edges. There was no exposed core material. That was part of the design and how we designed the form so that we were able to do that. And it felt really good to ride. So moving forward, we're actually now working with a startup in the States called Community Skate, and we're going to be further developing this board and trying to use even more natural fibers and a bio-based epoxy system. So yeah, that's everything from my side. Thank you very much. I'll hand it back over to Charlie now.
Thanks, Ben. That was really good. It was good to see you riding this board at the end. I've got quite a lot of questions here from people who've been watching, so I hope everybody found that interesting. I had first a few questions on data, which I think I will ask Charlie. So Charlie, you showed very rapidly the type of information you can find in Selector. There were a few questions on price. Where do we get this from? And do you get SN curve for these materials as well?
Okay, so on the price, so you've obviously noticed on the chart, one of the things we do quote within Material Universe is the price information. So the price information, this is actually created using, we have an internal price model. It's based on the material constituents. So for a metal alloy, it's the alloying elements. For a polymer, it's the base resin and any fillers, additives which are added to that resin. We get the prices of those constituents from the world commodity markets. We run those prices through our price model to come up with a relative pricing for the different materials. I should highlight the price isn't meant to represent the absolute price you expect to pay from your supplier. That will depend on the quantity you purchase and also your relationship with the supplier. The key thing about this is it enables you to very quickly do a cost-performance trade-off between the different material options. That's its primary purpose. Obviously, if there's only very small differences in price, that's not significant in terms of the accuracy of the model. We're looking for, should I be comparing, say, an aluminium alloy against a polymer? You're looking for significant differences in the price. It's very much this price-performance trade-off. So that's where the price information comes from. I think the second question was about whether we have fatigue or SN curves for the data. So we have within Material Universe, we quote the endurance limit for all the materials. So this is fatigue strength at 10 to the 7 cycles. But also for the metal alloys, we do have, I suppose it's a fairly simple model, which looks at the fatigue properties of the material. So here we've got a fatigue strength versus the number of cycles, and this gives you an indication of how the strength reduces with cycles. One here, you can also filter on this as well. So we have the fatigue strength at 10 to the 7 cycles. I can also change this parameter if I'm interested in, maybe 1,000 cycles. I can add that in. Then basically what happens when I do that is that this value now is read off this curve at this level, so we can actually compare the different materials at the different either stress ratio or different number of cycles. So that's supplied for the metal materials.
Okay, in terms of cost, there was another question from another attendee asking whether the costs are only consider the material cost, or whether there is a way to consider as well the processing cost when making a part.
Yeah, no, that's a good question. Within the price model, the information is actually the raw material. So that's for a polymer, it's the polymer pellet, and for the metal, it's the base material going into, say, the rolling process. So this is an early indication. Obviously, the final cost will depend on the material and the process chain. So on Material Universe, the initial price is based on the raw material. The keen-eyed of you may have spotted that within the synthesizer, we also have a part cost estimator. This is a tool which enables you to start to take a material and add in additional processes and it estimates the cost of that component. So we do have a tool in the synthesizer which enables you to start to consider the processing cost as well. But in terms of the material universe, which is the data set that we're using today, it does represent just the material price.
Excellent. I hope that was clear. I have a question about form. If the door is curved and can we use a honeycomb, is there a possibility to consider the form in the design?
That's a good question. Within the analysis, in the analysis I showed with these indices, so mass per unit of stiffness, here we were considering a flat panel. The same, if it was a curved panel, what happens that increases the I suppose the structural stiffness of the component. The index we use still applies whether it's a flat panel or a curved panel. So that's one thing, but I think here you're saying if you have a sandwich panel, you're using a honeycomb, then there's obviously restrictions in terms of the curvature of the honeycomb. So in this analysis, we essentially, the assumption is that it is flat, but obviously you can buy grades of honeycomb, you get a flex comb, things like that, which conform to double curvatures. So within this analysis, which is very much this early stage design, we are looking at the simple case. It's all about pointing you in the right direction. What you always need to do is, once you've identified a particular configuration, is you then need to find out more in-depth information about the different components.
Okay, I think I've got a question for Ben now, because it's about serial production. Is there any chance to adjust the manufacturing process in a way that near shape fabrication can be achieved and avoid the cutting and the milling, etc.? Ben, do you want to take this?
Yes, great. That's a good question, and that's really the challenge with composites, I think, is coming up with a affordable production process that doesn't cost millions in terms of tools, but that also has an acceptable cycle time. I think in this case, there is some waste material with the trimming, but I don't. I think it would be hard to actually make this board to shape without having any trimming. You could do it in a closed mold process, an RTM process, but when you do it that way, you start to spend more money on the tooling, and you also have a slower cycle time. I would imagine in this case where you have the core material as well as part of this RTM process. So, I think this is something we're going to be looking at with community skates in terms of how do we optimize this. And I think doing a vacuum infusion process like this, then you could probably infuse quite easily, 6 boards at once. And there are some other tricks you can do in terms of making the production process faster. But it would be tricky, I think, to reduce the amount of waste we have.
Thank you very much. And there is one last question. I don't know whether you or Charlie want to get that one. If we have a sandwich carbon flax foam, what about adhesions of the different materials to each other?
I mean, I'll be interested in your response to that, Ben, but I will mention something about the model, because we make assumptions in the models we implement in the synthesizer, and obviously it's important that people kind of understand the limitations of the system. So I'll address that, and then if Ben could respond with his take on the question about the more the technical side of it. In the synthesizer, one of the key things is, we do make assumptions. We have to make assumptions to simplify the calculations. So I should mention we have full traceability about the assumptions we make and also the calculations we use. So at the top of each of these models, we have a help icon, and here we actually list all the assumptions that we use in the calculations. So one of the things here is that for a sandwich panel, we assume that there's perfect interfacial bonding between the different layers, and also, so this gives you, clarifies exactly what is being considered within the calculation. We also assume that in a composite, the fibres are perfectly aligned. Obviously, in practice, these things often, don't work out that way. But also we detail all the calculations we actually use in the model. So there's full transparency in terms of how the model's working, what is and isn't actually included in the calculation. So it's worth highlighting that, because obviously, the model is only as good as the information you put in, but you do need to understand the limitations of it. And I guess the key thing here, again, it's all about identifying potential materials in the early stage of the design. So that's from the technical side in terms of the actual the model, what's been implemented. I mean, Ben, do you have any comment on the actual, I suppose, the detail of that interfacial bonding between the different layers?
Yeah, well, I think I'd just add to that's there's sort of a hidden third component when you talk about sandwich panels. It depends, of course, how it's made, but that's the adhesive between the core material and the face sheet. And that needs to be chosen correctly so that it has the appropriate shear strength and bonding characteristics. So that's if you have a core material like a honeycomb, perhaps, and then you definitely need to have that adhesive layer. But if you do an infusion process like we did, then the epoxy resin actually functions as that adhesive layer, and it does a fantastic job of bonding your different fiber layers together. So your carbon layer, your flax layer, and then the foam layer as well. It just gets all continuously bonded together. So that's the nice thing about doing it that way.
Okay, I think we've ran over a bit, so I think I will conclude now, and we'll wrap up. I just wanted to say thank you to everyone for attending. Thank you very much, Charlie and Ben, for presenting a very good case study and how it can be applied in real life. And thanks, everybody. And if you have any more questions, we will send the presentations to everyone who attended. If you have any more questions, please contact Ben or Charlie directly, as you can see there. Contact details here on the last slide. Thank you, everyone, and goodbye.
Thank you. Bye-bye.